So we're going to look at some specialist maths multi-choice questions from easy to hard. Interesting thing about the specialist maths multi-choice section is that the hardest questions are not necessarily at the end. What I've done here is pulled the data for the last 8 years of exams since 2016, and this is the average success rate on each question. So for example, question 1 had a 75% success rate, and in maths methods, question 1 had an 85% success rate. So interesting thing, if we look at the maths methods exams for the last 8 years, we can see that the hardest questions are almost always at the end of the multi-choice section. Whereas for specialist maths, that is not the case. And the hardest questions could really be anywhere throughout the 20 questions, probably not question 1, but because they tend to have been arranging the questions in study design order, the hardest questions may not be at the end, they could be anywhere. So it's a really important skill for you when you're working through them, not to get stuck or bogged down on any 1-mark question. If it is a really hard question, leave it and move on. If you run out of time, at least guess, and you may get lucky and guess 1 or 2 correct. You're not going to guess an extended response question correct, but you got a 1 in 4 chance of guessing a multi-choice question correct. All right, so here we are with the 2018 Specialist Maths Exam 2. We're going to look at the multi-choice questions from easiest to hardest. Easiest question on this exam was question 1. It was this question about the graph of half inverse tan of x, and the question was to find the equation of the asymptotes. So have a look. Pause the video if you like. It's option E. Sorry if you didn't have time to pause it. Inverse tan of x generally would have asymptotes at y equals pi on 2 and negative pi on 2. Because we've got a half there, then we're just halving the y values there. There's several ways we could do this question. We could graph it on the CAS calculator. We could even take a limit on the CAS calculator. So if we take a limit as x approaches infinity, we would find we approach pi on 4. So the easiest questions tend to be the questions where you can either just evaluate it quite quickly on your CAS calculator, or it's like straight application of a formula. So the next question we'll look at is question 11. This one, I was surprised actually how well this was done. So consider the vectors given by A and B. The acute angle between A and B is 30 degrees. Find M. Have a think about it if you like. The way we want to do it is apply the scalar product formula. So we know A dot B is equal to length of A times length of B cos theta. And we know theta is 30 degrees. We can easily work out A dot B multiplying the I coefficients and the J coefficients and adding them. Length of A using Pythagoras, square root m squared plus 1. And length of B is actually exactly the same thing. Cosine of 30 degrees is the square root of 3 over 2. But obviously we've got our calculator here, we could evaluate that. So we could solve that then on the CAS calculator, and you would find the answer is C. We could also do it by defining vectors A and B, then using the dot product function and the length function on the CAS calculator. All right, the next question we're going to look at is question 7. Curve is described parametrically by x is sine 2t, y equals 2 cos t, the length of the curve. So length of a curve is on the formula sheet for the parametric form. So students were able to recognize that, apply the formula. So here we would want integral of 0 to 2 pi, square root, dx dt we can probably do quite easily by hand as 2 cos 2t, and dy dt negative 2 sine t. Obviously we could also do these derivatives on the CAS calculator if you prefer. Type this onto the calculator with a decimal approximation, we should get 12.5. Okay, again, so straight application of a formula. The formula is on the formula sheet. That one was quite well done. All right, next up, question 14. Scalar resolute. So again, it's a straight application of a formula, but just to, in case you're not sure, scalar resolute, if we have two vectors A and B, the scalar resolute measures the projection of A onto B. Okay, so it's this length here. Now, actually, in this case, it turns out that the scalar resolute is negative. What that means is that A and B are pointing in different directions. So let me just redraw this. If we have this case, we project A onto B, it's actually being projected in the other direction. So this scalar resolute here would be negative. It's not really a length, but we can call it a signed length. And that would be our scalar resolute in this case. So the formula for scalar resolute is A dot product with the unit vector of B, or we can do it as A dot B over length of B. It's easy enough to do this by hand here. Dot product of A and B is -3, J component is 0, K component -6, divided by length of B, 1 squared plus 2 squared plus 3 squared, and we'll get -9/√14. We can also do that on the CAS calculator by defining A and B, and then using the dot products function. So if we define A as 3, 0, -2, not 30, B as -1, 2, 3. Okay, so then we want the dot product of A with the unit vector of B. The dot product and unit vector commands are there under the matrix and vector menu. Scroll down to vector, and there we are, unit vector dot product. I tend to just type it in, dot P and unit V, and there we go. So those functions can come in quite handy. All right, and the next easiest question was question 8. This is a U substitution question. Which of these is the correct U substitution for this integral? The key here is that sec squared is the derivative of tan. So if we let U be tan x, then du dx is sec squared. And that's great because we have sec squared there in our integral. So we can rewrite this whole integral as u squared du dx dx, which just becomes u squared du. Now we do need to change out the terminals as well. So when x is 0, tan of 0 will be 0. When x is pi on 6, tan of pi on 6 is 1/√3. These questions, even if you cannot evaluate the U substitution, if you can type it into your calculator and get a decimal, you can actually check all of these, and whichever one gives you the same decimal, that's then going to be your answer. So, no matter how hard the U substitution is, or no matter how confident you are with U substitutions, you can always check questions like this using your CAS calculator. So now we're up to the hard questions, what you've been waiting for. Starting with this one, question 4, a success rate of only 49%. Cos x equals -a, cot x equals b. Find cosec of -x. So this question, the CAS calculator is probably not much help. We just need to write these out using the relationship between cot, cos, and cosec. So for example, cot x, we can write as cos x over sin x. And we know cos x is -a, so -a over sin x is equal to b. Well, that's good because we divide through by -a, and we get 1 over sin x is equal to -b on a. So cosec of -x, well, that's going to be 1 over sine of -x, which is negative b over a. So we get a. So yeah, CAS calculator is probably not that much help there, which is probably why students find that difficult. Okay, next one we're going to look at is question 17. Oh, this question, yeah, so it's a kinematics question about a hot air balloon. It's ascending at 2 meters per second squared. Tourist drops the camera over when the balloon is 50 meters above the ground. Neglecting air resistance, sorry. The time for the taken to camera hit the ground. So the acceleration is -9.8. we have the constant acceleration formulas on the formula sheet. So we want to be using this formula here. Once we identify that, it's really just a matter of subbing in these values that we have and solving for t. So I'm not sure why students found this so hard. ut plus half a t squared. Acceleration is negative, so we're going to want this to be a negative displacement and just solve for t. All right, so we're getting 3.4. We can do this without a constant acceleration formula. If we just let a be negative 9.8, that is going to be d squared x dt squared. So we can anti-differentiate twice. dx dt will be negative 9.8t plus c. Now the initial velocity is 2 in the positive direction. Then we anti-diff again, we'll get negative 4.9 t squared plus 2t. If we say plus 50 and then solve for when x is equal to 0, we'll get the same thing. Okay, but why not just use the constant acceleration formula, because acceleration there is constant. Next, we're back all the way back to question 3. Question 3, not this one. Okay, this partial fractions question, and it's tricky because we've got a cube there in the denominator, which is not really normal. We don't usually have those, but which is the partial fraction form? So it turns out, actually, we can factorize the top line into 2x plus 1, x plus 1. Once we identify that, we can simplify this whole thing into 1 over 2x plus 1 squared, x minus 1. If we can identify that, we can then probably work that out by hand. But given that you have your CAS calculator for this, easiest method is just put this into an expand function. Okay, so if we can use the CAS calculator to expand the partial fractions, we get something that looks like option D there. I wouldn't expect you would have to do something with a cube on your exam 1. Next, we're still early on in the multiple choice section. We have question 5. Question 5, complex numbers question. Often the complex numbers on the multi-choice can be a little bit tricky. And like this one does involve a little bit of thinking. So z plus 1 over z is a real number. Which of the following must be true? So there's a few ways we can think about it. If we take it in Cartesian form, we'll have z plus 1 over z, so a plus bi plus 1 over a plus bi. And we know that this must be a real number, so the imaginary part of that is going to be 0. Now, from there, we could simplify this by multiplying top and bottom by the conjugate. But we can also simplify this on the CAS calculator, okay? So just typing in the imaginary part of a plus bi. So we have a function for the imaginary part of a complex number under menu, number, complex number tools, imaginary part, or we can just type imag. And if we just type all that in, we'll get this expression b minus b over a squared plus b squared. Okay, if we rearrange this a little bit, well, we can drag this term over to the other side and then we can cancel out the b's to recognize that a squared plus b squared must be equal to 1. So from that, if our complex number is a plus bi, we can see that the length of z must be equal to 1. We can also think about this question using polar form. And also a diagram, a little diagram might help. We've got our complex number z. If we represent that as r cis theta, then 1 on z is going to be z to the minus 1 is 1 over r cis negative theta. So the angle is going to be the negative of the first one. And What we want is when we add these two complex numbers together, we're going to end up on the real axis. We could recognize that's only going to work if their lengths are equal. If one is shorter than the other, we're not going to end up on the real axis. But looking at it algebraically, once we expand out the cos theta plus r sine theta, if we want the imaginary part to be 0, we want r sine theta plus 1 on r sine negative theta to be 0. Okay, because the imaginary part must be 0. Sine of negative theta is negative sine theta, so that would give us r minus 1 on r must equal to 0. And we can rearrange that to work out that r must be equal to 1. So that was a challenging question, but there are a few ways to do it, and the calculator can help. Drawing a diagram is also good advice for any time we have anything geometric. And the last question we'll look at, the hardest question on this paper, was question 12, the question that students found the hardest. To me, I'm not sure why this was so challenging, but length of A plus B is equal to length of A plus length of B, which of the following is necessarily true? Well, I guess to start with, anytime we have a question about like which one of these is true, which one of these is false, it is going to be a little bit more time consuming because we need to check through every option and sort of rule them out, or in this case, find one that's true. But we don't have to look very far because it turns out if A plus B, so let's draw a diagram. We have vector A here, and imagine they're not parallel, vector B. Well, A plus B is going to be this vector here. Clearly, if this is a triangle here, the length of A plus B is going to be less than the length of A plus the length of B. This is called a triangle inequality. So the only way that they can actually be equal is if A is parallel to B. So again, CAS calculator is probably not that useful in that question. It does involve a little bit of thinking. Drawing a diagram helps, so that's always good advice. All right, so just in case those questions were not hard enough for you, we're going to have a look at the hardest multiple choice question in the last 10 years. This question had a 6% success rate. So it's this question here from the 2017 exam, and 6% is really ridiculously low when you think about 5 options. I mean, if you're just guessing, you got a 20% chance, but clearly there's a lot going on here. We've got a function f, its derivative and second derivative. We've got some information here. We've got a function for the second derivative, and we're being asked about the coordinates of points of inflection of mod f of x. So firstly, the key for this question is knowing what is a point of inflection. Point of inflection means a concavity change. I.e. the second derivative changes sign. Meaning either the second derivative was positive and then we changed to negative, or the other way around, negative to positive. Let's have a look at the information we have. We have this function for the second derivative. Well, it's defined in terms of another function, g of x, where we're told g of x is less than 0. But we can easily identify when this function is going to be 0. It's going to be 0 when x is equal to negative a or x is equal to b. Just drag that out from under my head. But at which of these points does the concavity actually change? Well, it only changes when x is equal to b. Okay, because at x is equal to negative a, this graph would touch on the axis and then turn around again. If we think about a graph of f double dash, it's going to touch and turn at negative a. Well, actually, g of x is less than 0, so it's going to be upside down. Something like that. We'll cross at b, you've got an intercept at b, but at a we've got a turning point there. So the second derivative does not change sign here, but here it changes sign from negative to positive. So we're looking for only x is equal to b. Out of options b and e, we choose e because this is a modulus function, it's never going to be negative. The y value there is positive 1. Definitely a challenging question, but I think the key thing is being aware what is actually a point of inflection and knowing that what that means is the second derivative must change sign. Second derivative must change sign. Second derivative must change sign.